Mathematical induction. This is today's topic which we are going to deal with. What is mathematical induction? When can you use it? And what are its benefits? This is a technology of proving a statement which is already established. You cannot find out new formulas using this technology. Okay, so it is used for proving already known results. So it is a technology for proving a statement or a formula or a theorem which is thought to be true, which is thought to be true for every natural number, for every natural number n. So I suppose you remember what is n. N does not involve 0. Other than 0, it will go from 1, 2, 3, etc. And natural numbers are countable. Right. So, under this, we are going to see the first principle of mathematical induction. What does this principle say? The first principle of mathematical induction says, let P of n be a proposition, let P of n be a proposition corresponding to positive integers, corresponding to positive integers. Say n. Then, number one, if P of n naught is true, if P of n naught is true for some for some integer n naught, and if P of k is true for an arbitrary integer k which is greater than n naught, then we can say that P of k plus 1 is also true. Then we conclude P of n is true for all integers n greater than or equal to n naught. This is the first principle of mathematical induction. So based on the first principle of mathematical induction, let us go into say some one or two problems which may make you familiar with this concept. The first problem to be treated under this topic, let us consider a simple problem which says if n is a positive integer, if n is a positive integer, then show that 1 plus 2 plus 3 plus etc. up to n is equal to n into n plus 1 whole divided by 2. N into n plus 1 divided by 2. See, you are only establishing an already known result. Okay. Now, this step actually comprises of three stages. One is known as the basis step and the second is known as an inductive step. What is this basis step? The basis step is the smallest integer which you are going to consider for which this is going to hold true. So now for the solution, let us denote by P of n 1 plus 2 plus etc. plus n equal to n into n plus 1 divided by 2. Now, what is it that we have to prove? We have to prove P of n is true for all n greater than or equal to 1. So the basis step, what is the smallest value that n can take? It is 1. So in your basis step, we have to consider put n equal to 1. Then what happens in this? My p of 1, p of n is n into n plus 1 by 2. My p of 1 will be 1 into 1 plus 1 divided by 2, which is equal to 1. And incidentally, the first term here is also 1. Therefore, it is satisfied, or we simply say P of 1 is true. The next, we have to go for the inductive step. What is this inductive step? We assume the result is true for an arbitrary k and try to show it is true for k plus 1. So, assume P of k is true for k greater than 1. That is 1 plus 2 plus etc. plus k. This is nothing but k into k plus 1 whole divided by 2. Let me take this as equation number 1. Now what I have to prove? I have to prove 1 plus 2 plus etc. plus k plus 1 is equal to k plus 1 into k plus 2 divided by 2. This is what I have to prove. So let us consider 1 plus 2 plus 3 plus etc. plus k plus 1. I am considering my left hand side series. Now what I am going to do with this, I am going to club the first k terms and substitute this with equation 1. What is my equation 1? My equation 1 reads 1 plus 2 plus etc. k is k into k plus 1 by 2. Substituting that, I will have k into k plus 1 by 2 plus I am going to have a k plus 1. Now let us take LCM for this. So this is k into k plus 1 plus k plus 1 into 2. Am I correct? Whole divided by 2. So k plus 1 is a common factor. Pull it outside. So this would become k plus 1 into k plus 2 whole divided by 2. Therefore, my p of k plus 1 is true. And this is what I need to establish. Hence, by mathematical induction, I represent it as capital MI. P of n is true for every n greater than or equal to 1. This is what we need to show. Let us now go on to the second example. Say, use mathematical induction. I represent it as capital MI to prove the number 9 divides n cube plus n plus 1 the whole cube plus n plus 2 the whole cube whenever n is a non-negative integer. Whenever n is a non-negative integer. This line is very important for us to determine our basis. Okay. So first thing is we should coin what is our p of n. So let p of n be this value n cube plus n plus 1 the whole cube plus n plus 2 the whole cube is divisible by 9. Okay. So this is my p of n. Now what happens when I choose my basis? It is non-negative integer. The word non-negative integer says 0 is also included for me. So my basis condition, I have to take n not equal to 0 or my p of 0 value. My p of 0 will be equal to n cube 0 cube n plus 1 the whole cube, 0 plus 1 the whole cube, n plus 2 the whole cube, 0 plus 2 the whole cube. So this is going to be 1 plus 8, which is equal to 9. Therefore, we can easily see P of 0 equal to 9 is divisible by 9, is divisible by 9. Therefore, basis is true. I have proved that the basis is true. Next, I have to go for the induction step. So what is the induction step or the inductive step? In my inductive step, I will assume the result is true for an arbitrary k. That means we are going to assume P of k is true for k greater than 0. Now I'm going to assume 9 divides k cube plus k plus 1 the whole cube. Okay, my values are not coming right. So k plus 1 the whole cube plus k plus 2 the whole cube. In other words, I can say this as k cube plus k plus 1 the whole cube plus k plus 2 the whole cube is divisible by 9, or this is going to be a number which is going to be a multiple of 9, say 9x. I take this as equation number 1, where my x belongs to z plus. Now, I need to prove P of k plus 1 is true. That means it is also going to be divisible by 9. Okay, so I have to show, that is, I have to show P of k plus 1 is divisible by 9. How do I show this? Now, in the place of k, I have to replace k plus 1. Consider this. This would be k plus 1 the whole cube. Then k plus 1 plus 1. Then it will be k plus 2 the whole cube. Plus it will be k plus 2 plus 1. K plus 3 the whole cube. Now let us try to expand this. How can I expand this? What I do is I substitute for k plus 1 whole cube plus k plus 2 whole cube from this first equation. What is this? This is 9x minus k cube. So this could be written as 9x minus k cube plus k plus 3 the whole cube. Now start expanding. So my p of k plus 1 is now 9x minus k cube plus I have k plus 3 the whole cube. What do I know? I know that my a plus b whole cube is a cube plus 3a squared b plus 3ab squared plus b cube. Now let us try to incorporate it here. I will have 9x minus k cube plus k cube plus 27 plus 9k plus 3k squared. Am I correct? Is it 3k squared or is it going to be 9k squared? It's going to be 3 into 3k squared. So this would be 9k squared. So now let us check what happens. Again here it is going to be 27k. So if I'm going to write it properly, 1 minute, it's going to be k cube 3 into a squared b. So this is 9k squared. Then plus b cube. B cube is 3 cube, that is 27, plus 3ab squared. So 3 into k into 9. So it is going to be 27k. Now let us consider this. We can take k cube gets cancelled, positive k cube, negative k cube. There is going to be 9 common in all these terms. So I will have 9 into x plus 9 into 3 is 27. So plus 3 plus k squared plus I am going to have a 3k. Clearly, This is of the form sum 9 into y. Therefore, my p of k plus 1 is also divisible by 9. Hence, by mathematical induction, what can I say? 9 divides n cube, 9 divides n cube plus n plus 1 the whole cube plus n plus 2 the whole cube for every n greater than or equal to 0. This would be my conclusion. I have think we have seen two sums which are very similar to each other. Now let us proceed to the next example. Example number 3. Prove that prove that this is given by 1 divided by 1 into 3 plus 1 divided by 3 into 5 plus 1 divided by 5 into 7 plus etc. 1 divided by the general term is 2n minus 1 into 2n plus 1, okay, equal to n divided by 2n plus 1 for every n greater than or equal to 1. Now, every n greater than or equal to 1 is given to us. So, in basis, I have to consider n is equal to 1 for this problem. We shall start the solution. Let P of n be the given. So, P of n denotes the same thing given on top, 1 divided by 1 into 3, 1 divided by 3 into 5 plus etc. plus 1 divided by 2n minus 1 into 2n plus 1 equal to n divided by 2n plus 1 for all n greater than or equal to 1. Now, what do I have to prove? I have to prove P of n is true for every n greater than equal to 1. So to start, I have to try with the basis. What is the base number here? It starts from n equal to 1. So I have to take my n naught is equal to 1. So initially, I will have P of 1. P of 1 will be 1 divided by n is 1, 2n. N divided by 2n plus 1, that is 1 divided by 2 plus 1, which is nothing but 1 divided by 1 into 3. 3 is the same as 1 into 3. Therefore, the right hand side and the first term in the left hand side tally. The first term in the left hand side is 1 divided by 1 into 3. Hence, I claim P of 1 is true. We go to prove the inductive step. What is this inductive step? We will assume P of k is true. We will assume P of k is true for k belonging to set of positive integers and prove P of k plus 1 is true. Okay. And we need to prove and we need to prove P of k plus 1 is true. Alright. Now consider 1 divided by 1 into 3 plus 1 divided by 3 into 5 plus etc. plus 1 divided by 2k minus 1 into 2k plus 1 equal to k divided by 2k plus 1. So it is k divided by 2k plus 1. We are taking this to be our equation number 1. Okay. Now I have to consider P of k plus 1. So what will be this P of k plus 1? It's going to have an added term to the above. So it is 1 divided by 1 into 3 plus 1 divided by 3 into 5 plus etc. plus 1 divided by 2k minus 1 into 2k plus 1 plus I have to write a k plus 1th term. Wherever there is k, put k plus 1. So this first 2k minus 1 will become 2k plus 2 minus 1 into 2k plus 2 plus 1. So this is now going to be equal to, I'm going to substitute for all these terms over here from equation number 1. So this is going to be equal to k divided by 2k plus 1 plus 1 divided by, I will have 2k plus 1 into, I'm going to have 2k plus 3. Now let us try to simplify this. If I take LCM, this is going to be 3k plus, I will not have it as just 3k plus 1 plus 2k squared. This would be my numerator plus 2k squared divided by, I will have 2k plus 1 into 2k plus 3. Now let us resolve this. So my p of k plus 1, I had got it as, just for our recollection, I had k divided by 2k plus 1 plus I had 1 divided by 2k plus 1 into 2k plus 3. So this is k into 2k plus 3 plus 2k plus 1. We are taking LCM divided by 2k plus 1 into 2k plus 3. Now this results in 2k squared plus 3k plus 1 divided by, I will have 2k plus 1 into 2k plus 3. Try to factorize the numerator. This gets factorized to be k plus 1 into 2k plus 1 divided by 2k plus 1 into 2k plus 3. So my 2k plus 1 gets cancelled to give me k plus 1 divided by 2k plus 3. How can I rewrite this? I may rewrite this as k plus 1 divided by 2 into k plus 1 plus 1. In other words, some capital N divided by 2n plus 1, where n is k plus 1. Okay, where my n is k plus 1. Therefore, therefore, Rp of k plus 1 is true. Hence, by mathematical induction, the result is true. The result is true for all n greater than or equal to 1. This is what we wanted to show. Okay. I suppose now you are feeling more familiar with this topic. Let us look into some more problems under the category. So, example number 4. Prove that 1 into 1 factorial plus 2 into 2 factorial plus etc. plus n into n factorial equal to n plus 1 factorial minus 1, where n is a positive integer, where n is a positive integer. This word is very, very important for us to determine our basis. If the word is positive integer, you have to start with 1. If it is non-negative integer, you have to start with 0. Okay. So now let us look into the solution of the problem. So let P of n denote the given proposition. Let P of n denote the given proposition. Okay. Then what would be your basis step? We have to prove P of n is true for all n greater than equal to 1. So your basis step would be P of 1. So that is 1 into 1 factorial. And this is the same value 1 into 1 factorial. Come for your LHS and your RHS. Your right hand side is n plus 1 factorial minus 1. The RHS is n plus 1 factorial minus 1. So in this case, it is 1 plus 1 factorial minus 1 or 2 minus 1 equal to 1. Therefore, this is nothing but our P of 1 value, and hence I declare basis is true. Okay. Once we show the basis, we have to move on to our inductive step. So what do we have to do in inductive step? We have to assume P of k is true for arbitrary integer k. In this case, our k belong to z positive. That is positive set of integers. So 1 into 1 factorial, 2 into 2 factorial, etc. I have to go for k. I have to go for k into k factorial. This value is nothing but k plus 1 factorial minus 1. This I have to assume it is true. Let me take it as equation number 1. I have to find out my p of k plus 1 and verify the result. My p of k plus 1 is 1 into 1 factorial, 2 into 2 factorial, etc. K into k factorial plus one more term k plus 1 into k plus 1 factorial. Now what I will do, I will club the first k terms and replace it with equation 1. So it is k plus 1 factorial minus 1 plus k plus 1 into k plus 1 factorial. Now in this you can take k plus 1 factorial as a common term. You will get it as k plus 1 factorial into 1 plus k plus 1 minus 1. So this is k plus 1 factorial into k plus 2 minus 1. This in other words is nothing but k plus 1 plus 1 factorial. Am I correct? This in other words is k plus 2 factorial minus 1. That is my p of k plus 1 is nothing but k plus 1 factorial minus 1, and this is what we actually need to prove. Therefore, p of k plus 1 is true. Hence, by mathematical induction, the result is true. By mathematical induction, the result is true. Okay, so these are all very straightforward problems where we were able to get the result just by back substitution. Now let us see some problems where we may have to think a bit. Okay, so this is our fifth example. Prove that 2 power n is strictly less than n factorial for every n greater than or equal to 4. See, here our basis, what number we should consider our n naught to be. Here the range starts only from 4. So n naught will be 4. Okay. So as usual, let P of n be the given proposition. Let P of n be the given proposition. Two power n is strictly less than n factorial for every n greater than or equal to 4. Now let me go to my basis step. My range is starting from 4, so I will have my n naught value to be equal to 4. Therefore, my P of 4, this is what I have to consider. What is this? 2 power 4, which is 16. Similarly, the right hand side, I need n factorial. which is nothing but 4 factorial. What is my 4 factorial? Value is 24. Therefore, I could give you, what could I give you? My 2 power 4 is strictly less than 4 factorial, or simply basis is true. So next we go for the inductive step. What to be done in this inductive step? We have to assume P of k is true. We have to assume P of k is true for some k in Z plus, which is greater than 4, which is greater than 4, and we need to prove P of k plus 1 is true. So P of k plus 1 is true means I have to prove 2 to the power of k plus 1 is strictly less than k plus 1 factorial. This is what I have to prove. So let me say consider 2 power k plus 1. How can I rewrite this? I can rewrite this as 2 to the power of k into 2. Simplest. So this is now strictly less than, what can I say? K factorial into 2. Why? I know that 2 power k is strictly less than k factorial. Therefore, it follows that this 2 power k is strictly less than k factorial. So when I multiply this, replace this 2 power k by k factorial, that will be a bigger number. Hence, what can I say more about this? If this 2 power k plus 1 is less than 2 into k factorial, it is going to be strictly less than k plus 1 factorial. How am I coming to this conclusion? Because k takes values more than 4. So definitely k plus 1 into k factorial means minimum 5 into k factorial if we consider also. It is going to be greater than 2 into k factorial. Hence 2 power k plus 1 is strictly less than k plus 1 factorial. Therefore, P of k plus 1 is true. By mathematical induction, my P of n is true for every n greater than or equal to 4. See, in this problem also we have done substitution only, but it should strike to you to analyze that 2 k plus 1 is strictly greater than 2. That you should remember. Since you are going to have definitely my k value greater than 4, at least greater than 1, then my k plus 1 is strictly greater than or equal to 2. Because where is my k starting? 4, isn't it? So if it's greater than 4, k plus 1 is strictly greater than 2, which confirms that by mathematical induction, this result is true. Okay, next. We move on to the sixth example. The sixth example is given by, show that 1 divided by 2 into 3 divided by 4 into 5 divided by 6 into etc. 2n minus 1 divided by 2n is strictly less than 1 divided by square root of 3n plus 1 for n greater than 1 by mathematical induction. Okay. So let P of n be the given proposition. Okay. So let P of n be the given proposition. Now I have to consider the basis step. Now look, it is given n is strictly greater than 1. So the range is starting from 2. So here n naught will be 2. So the basis step n naught is equal to 2. So what is my P of 2? My P of 2 would be 1 by 2, first number. The second one, if I have to calculate from the general term, it is 2 into 2 minus 1 divided by 2 into 2. I am taking n is equal to 2. So this is going to be 1 by 2. 2 into 1 is 2 divided by 4. So it is 1 by 2 into 2 into 2 minus 1. So 4 minus 1, it is going to be 3 divided by 4 into 2. Value is 3 by 8. Let us consider the RHS 1 divided by square root of 3n plus 1. So this is nothing but 1 divided by square root of 6 plus 1 or 1 divided by square root of 7. Therefore, clearly you can see that my 3 by 8 is strictly less than 1 divided by square root of 7. How do I get this? 7 nines are 63. Okay, I'm squaring both sides. I know that 63 is strictly less than 64 is true. Alright, just cross multiply and square. See, I have 3 by 8 strictly less than 1 by root 7. Square, you will get 9 divided by 64 strictly less than 1 by 7. What does this imply? 7 nines are 63. 63 is strictly less than 64. Therefore, I can clearly conclude my basis is true. Okay. That is, I have shown P of 2 is true. Next, what I have to show? I have to go for the inductive step. How to show this in my inductive step? So we assume P of k is true. Assume P of k is true for k greater than 1. So I will have 1 by 2 into 3 by 4 into etc. 2k minus 1 by k is strictly less than 1 divided by square root of 3k plus 1. Okay, we are going to take this to be true. So let me take it as my equation number 1. Next, I have to prove P of k plus 1 is true. P of k plus 1 is true. So what is this? My P of k plus 1, I have to rewrite this. So this would be 1 by 2 into 3 by 4 into etc. 2 into k plus 1. Okay. So I will have 2 into k plus 1. So this should be 2k minus 1 will now become 2 into k plus 1 minus 1, which is nothing but 2k plus 1 divided by, in the denominator, I should have 2k. Isn't it? K is replaced by k plus 1 divided by k plus 1. Okay. This is strictly less than, I have to consider my right hand side. This is what I have to prove. 1 divided by square root of 3 into k plus 1. So it would be 3k plus 4. Actually speaking, if I have to show directly, this is what I have to show. So how are we actually going to go about this problem? We need to make some juggling with our equation 1 in order to show the result. What we can try to do is, we will multiply and divide the left hand side by 2k plus 1 by 2k plus 2 on both sides of the equation 1. Then we will try to compare with this and find out how to get the solution. So in order to resolve this problem, please look, I am checking here, it is 2n whilst resolving. Here it should have been 2k. So here also it would have been 2 into k plus 1. Right. So now consider this. We will consider or multiply equation 1. We will multiply equation 1 by 2k plus 1 divided by 2 into k plus 1 is 2k plus 2. This we will do. So I will have 1 by 2 into 3 by 4 into etc. 2k minus 1 divided by k. I am multiplying into 2k plus 1 divided by 2k plus 2. So this is less than what I do to the left hand side, I have to do to the right hand side of the equation. So I will have 2k plus 1 divided by 2k plus 2 into square root of, I will have 3k plus 1. Okay. So let us consider this equation as equation number 3. And let us take the other equation maybe as equation number 2. Now, comparing the right hand side of 2 and 3. So, compare the right hand side of equation 2 and equation 3. What happens? I can definitely say my 2k plus 1 divided by 2k plus 2 into square root of 3k plus 1 is going to be strictly less than, it's going to be strictly less than 1 divided by square root of 3k plus 4. How am I coming to this conclusion? The conclusion I reach here is by taking the reverse. That is, I want to see if the converse is true or not, and then I come to my conclusion here. So, what would be the converse? Suppose that it is not true. So, I write, suppose not. Then, what happens? What will happen? I will get the reverse inequality. So, it will be 2k plus 1 divided by 2k plus 2 into square root of 3k plus 1 is greater than or equal to 1 divided by square root of 3k plus 4. Now let us try to simplify this expression. So cross multiply, I will get 2k plus 1 into square root of 3k plus 4, which is greater than or equal to 2k plus 2 into square root of 3k plus 1. If I keep simplifying this, I will get 12k cube plus 28k squared. I square on both sides and then I expand, plus 19k plus 4 is greater than or equal to 12k cube plus 28k squared plus 20k plus 4. Okay. So this implies 0 is greater than or equal to k. Okay. So this implies 0 is greater than or equal to k, which is not our assumption, right? Which contradicts our k greater than equal to, our k is greater than 2, which contradicts our k greater than 2. Therefore, assumption is wrong. Therefore, assumption is wrong, which in other words tells me that my 2k plus 1, see, which in other words tells me that this is correct. 2k plus 1 by 2k plus 2 into square root of 3k plus 1 less than 1 divided by square root of 3k plus 4. So this tells me 2k plus 1 divided by 2k plus 2 into square root of 3k plus 1 is strictly less than 1 divided by square root of 3k plus 4. Therefore, my P of k plus 1 is true. Hence, by mathematical induction, the result is true for all k. The result is true for all k greater than 2. This is what we have to establish. This particular problem we had to expand, we had to multiply. All this you will get it only through practice. Okay, next. All of you will be familiar with De Morgan's laws as we have already dealt with set theory in our unit 1. Okay. Based on that, let us try to prove the result using mathematical induction. So this is going to be our example 7. So let capital A1, A2, etc. An be any n set. Proof by mathematical induction. Proof by mathematical induction. Union I equals 1 to n an, the whole complement I am representing by a bar, is equal to intersection I equals 1 to n ai bar. Okay. Please note, on the right hand side the complement is inclusive of the operator union. In the right hand side it is excluding the operator. Okay. Solution. How are we going to give the solution? It is true for all n greater than equal to 1. So this is for all n greater than or equal to 1. So in my basis step, I have to start with n equal to 1 or n naught is equal to 1. So what would be my P of 1? My P of 1 would be, this is A1 whole bar. There is no union because only one set. Neither there is an intersection. Therefore, this is equal to the RHS A1 complement. Therefore, my P of 1 is true. Inductive step. Suppose you have to set, then also you can show it is true. So we assume for any k, assume P of k is true. Assume P of k is true for k greater than 1. That means I have union I equals 1 to k ai whole complement equal to intersection I equals 1 to k ai complement. So this is true. Let me take this as my equation number 1. I have to prove P of k plus 1 is true. So how do I prove P of k plus 1 is true? Union I equals 1 to k plus 1 ak whole complement. How can I rewrite this? I will rewrite this as I equals 1 to k ak union, this is, I'm sorry, ai union a last index k plus 1 with the whole complement. Once I am able to write it this way, now see, it is true up to k. 2 is definitely less than k. This is one set, this is one set. So this, in other words, I can rewrite this as A1 union A2 union etc. union AK whole thing together union A k plus 1, and I have my whole complement. because union is associative, that is also true. So this, in other words, is A1 bar union A2 bar union etc. union AK bar. Am I correct? Intersection A K plus 1 bar. How did I get to this step directly? Actually, what will happen? I have to take all this. I will connect it by a complement to overall over here and then say I know that this is true by De Morgan's laws. This is true by my De Morgan's laws for two set. One set is this whole thing and the last second set is AK plus 1. So this is true. Now we can break this up because we know union is associative. So we can have A1 bar, union A2 bar, union etc. union AK bar. Is it so? When you break this, what actually happens is the union becomes intersection because you will keep applying this De Morgan's law again and again. Now you have A1, A2, etc. AK. You will consider A1, A2, etc. AK minus 1 and AK separately apply. So when you go like this is A1 bar, intersection A2 bar, intersection etc. intersection AK bar, intersection AK plus 1 bar. This, in other words, is intersection AI bar. I is running from 1 to K plus 1. So this intersection I equals 1 to K plus 1 AI bar is what we have to show. Therefore, P of K plus 1 is true. So by mathematical induction, the result is true. I hope you understand. We are splitting the n plus 1 set as two sets. Okay, or here k plus 1 set as two set, one running from 1 to k, and the last one is a k plus 1. Then it is now considered as two subset. For that, you can apply De Morgan's law. What is your De Morgan's law telling you? My De Morgan's law is telling me A union B whole complement is A complement intersection B complement. So we apply A union B whole complement equal to A complement intersection B complement. Keep applying this over and over again. We end up with the required result. Okay. One more last type of problem which talks about divisibility. With this, we will be completely covering all possible types, probably under the first principle of mathematical induction. So, use mathematical induction to prove 3 power n plus 7 power n minus 2 is divisible by 8 is divisible by 8 for all n greater than or equal to 1. Since greater than or equal to 1 is given, our basis should be n not equal to 1. So let P of n be 3 power n plus 7 power n minus 2 is divisible by 8. So I may rewrite this as equal to some 8x. We will take this as equation number 1, or rather a notation for P of n. Okay. So maybe as 1, or we can even leave it like this. Now I need to go to the basis step. What I have to do in the basis step? I have to choose my n naught, the minimum value, that is 1. What I know about P of 1? It is 3 power n, so 3 power 1 plus 7 power n, 7 power 1 minus 2, the value is 8. And 8 is divisible by 8. Therefore, our basis is true. Okay. Next, inductive step. So when I go to my inductive step, I should assume that my P of k is true. Am I right? So inductive step, assume P of k is true for my k greater than 1. So I have 3 power k plus 7 power k minus 2 is equal to some 8 into m, where m is a positive integer. So let me take this as my equation number 1. Now I have to prove P of k plus 1 is true. So consider P of k plus 1. This is 3 power k plus 1, 7 power k plus 1 minus 2. So how can I rewrite this? I know that 3 power k plus 7 power k minus 2 is 8m. So I have to incorporate this 8m somewhere inside. So I will rewrite say 3 power k plus 1 as 3 into 3 power k plus 7 power k plus 1 minus 2. So this would be 3 into, from equation 1, this is 8m minus 7k plus 2 plus 7 to the power of k plus 1 minus 2. So this, in other words, is 3 into 8m. I have a 7 power k here. Let me take this 7 power k common. This is 7 power k plus 1, so I will have a 7 minus 3. 3 into 2 is 6 plus 6 minus 2. So look at this. This is 3 into 8m plus 7 power k into 7 minus 3 is 4 plus 4. Now let us try to combine these terms. So this is 3 into 8m. Then I will have plus 4 into 7 power k plus 1. Now 7 power k is going to be odd for all k. Okay, this is odd for all k. See, 7 power 1 is 7. 7 squared is 49 and so on. Okay, so 7 power k plus 1 is going to be even. Therefore, it is of the form, since it's an even number, you may write it as some 2l, where l belong to z plus. Hence, my p of k plus 1 would be 3 into 8m plus 4 into 2l. So this is 8 into 3m plus 4 into 2 is 8 into L, which is divisible by 8. Hence, P of k is true. By mathematical induction, the result is true. The result is true. With this, we come to the end of first principle of mathematical induction and problems based on the first principle of mathematical induction. Later in the next video, maybe we will check for second principle of mathematical induction.